Alright, welcome to page 3 now. So we're already on page 3 of 4. So again, the notes aren't going to take too long, but now we're going to talk about the midpoint rule. And the midpoint rule is very similar to the Riemann sums. We're going to, instead of taking the lower left, the lower right, the upper right, or the upper left, what we're going to do is we're going to take the actual midpoint or the middle part of each rectangle. So of each like little rectangle, whoa, don't want that. So these little rectangles that we're going to do, instead of taking it, at these upper right hand, spots, or, lower left, we're going to just take the middle or the midpoint of each subrectangle. That's the midpoint rule. So everything is going to be the same except for now we're taking the middle value. The thing is, all the other rules apply to double integrals. So like the midpoint rule we're using, it has applications with, the double derivative. The trapezoidal rule we could use for the double derivative, and Simpson's rule. I don't know if you did Simpson's rule for Calc 1 and 2, or mainly Calc 1, because Riemann sums is a Calc 1 topic. But we can apply all those rules to double integrals. So again, the midpoint rule for double integrals is the exact same, except for this is going to represent the midpoint, where you're going to have x bar, x sub I bar, y sub j bar. And those are just going to be the midpoints for each x and y component. All right, so let's go ahead and do example 2. Use the midpoint rule to estimate the volume in part A. So what I'm going to do is I'm just going to rewrite or redraw that rectangle. And again, we were at we were at 1, 2, and then that was 1, 2, 3. And those are our subrectangles at 1.5 and again at 1.5. Alright, and so now we're going to take the midpoints to find our Riemann sum. So the midpoint of each of those values. Alright, for our subrectangles, our delta A is going to still be the same. Alright, each rectangle is going to a width or a delta X of 0.5 and a length for over our Y of 1.5. So our delta A is still going to be 3/4. I should remember what it was. Alright. And now let's go ahead and take the volume. And again, you can skip when I'm writing out the notation. So the double integral of 1 plus x squared plus 3y, so of our function, dA, is approximately I equals 1, 2, j equals 1, 2, f of x bar, y j bar, j bar times delta A. And so now we're just going to have, so our values are going to be f of 1.25 times, and the middle value, it's really not 1, it's like 0.75 or 3/4, times our delta A. I'll just write that out. Plus f of, and so our next one's going to be 1.25, and then the next one's going to be 2.25 times delta A, plus f of 1.75 times times 0.75 delta A. Running out of room on the f of 1.75 2.25 times delta A. I just barely made it, and I say barely because that looks awful at the end. Alright, now I could pull out a delta A. So this time I'm just going to go ahead and pull out my delta A. Remember, all my delta A's are 3/4, so I'm just going to pull out the delta A and have 3/4 on the outside. That way I can just do all the heights individually. So the height of, so when I plug in 1.25 and 0.75 back into the function, back into this function, alright, I'm going to get the height. And so the height, when I plug that back in, is going to be 77/16. Plus, now I'm going to do the height when I plug in 1.25 and 2.25. When I plug that in, I get 149/16. When I plug in 1.75 and 0.75, I get 101/16. And when I plug in 1.75 and 2.25, I'm going to get 173/16. That's not a 3, that's a 6. 173/16. Alright, let me check my work real quick. 77, 149, 101, and 173. Alright. So, when I multiply all those, again, you can use a calculator to do that. I get 375/16. And that's going to be equal to 23.4375. Alright, and again, either of those can be your answer. Alright, so hopefully you're seeing that, oh, hey, this is not bad. And you're right, it's not that bad. Alright, let's go ahead and look at average values, and then we'll end page 3. And then we'll go off to page 4. So recall that the average value of a function f of one variable defined on an interval. To find the average value, all we did was we took our integral and we divided by the total, the length of how far we're going along the x-axis. And we did b minus a, so that total, how far the integral goes, we just divided by that. Well, to do the average value, instead of taking, dividing by the entire length, here we're going to divide by the entire area of our rectangle. So that's what this means. A of r is just the area of the entire rectangle. So to find the average value, we're just going to divide everything by the average of the average. In order to find the average value, all we're doing is we're going to divide our double integral by the total area of our rectangle. That's it. All right. That's about it. It says if f of xy is greater than or equal to 0, then the equation, so we could, do the area of our total times the f ab is equal to the double integral of our function dA. It says that the box with base r and a height of the average height has the volume as a solid that lies on